What's the definition of a failure? Say that we have a natural slope. This is the natural soil slope. And we're building a structure to the top of the slope, and depending on the weight of that structure, you may increase, certainly you increase the stress at the soil. Maybe here, maybe here, maybe here too. Right. Initially, the stress, the vertical stress was sigma naught, and because of this foundation and the upper structural weight, it will increase the stress by delta sigma, right? Then, if the delta sigma exceeds the certain level or the threshold value, the material can sustain or resist, then you develop failure. The soil will slide for this condition. It's easy to slide down because of the weight. Then, when you look at closely at the failure envelope or failure line, you have a failure surface like that, and each soil is failed, right? Because of the excessive stress. So we need to find out how much this soil can sustain, how much stress increase the soil can sustain. Or can we predict the stress condition that caused the failure? Then we can compare that the failure condition stress to the initial or the current stress condition and see how much more load can be better or can be sustained by this soil. So in this chapter, first one is to find out the stress condition. That is our first question. And then we're going to compare to the soil strength, whether this is larger than the strength or still less than the strength of the state. So that will be our main question of this chapter. So let's define the failure first. So failure is when the deformation becomes unacceptably large, and it's referred to as failure. So as long as whenever there's a stress increase, you have deformation because material is not perfectly rigid. So that deformation is that deformation acceptable or not determines whether it is affect the material, the media, or the ground, or the structure is failed or not. So strength of material is defined as the maximum stress that the material can sustain without failure. Let's go back to this natural slope case. When you closely look at the soil here, there's a failure envelope. Initially, before the failure occurred, there's a sigma B and sigma H. The vertical stress and the horizontal stress at that soil mass. Suddenly, because of this sigma, so it failed along this failure line. This is failure for the failure plate. So, then when we look at this failure plane, there should be a normal stress, sigma n, right? Normal stress and the shear stress, tau n. This failure plane. So, whether this sigma n is larger than the compressive strength of the material, or whether this shear stress is larger than the shear strength of the material, right? Either that or other of that case will cause the failure. In general, shear strength is much larger than, much less than the compressive strength in the soil. So, in general, so that means the shear strength and the shear stress determines the failure condition. So in this soil map, if the tau n is getting larger than the shear strength of the soil, then soil will fail. If less than that, soil can resist or sustain those failure of. So in the soil mechanics or in geotechnical engineering, in terms of the strength, we look at the strength criteria. Shear strength is the most important. It's not the compressive strength or tensile strength. We only look at the shear strength because shear is the weakest part. It's certainly easy to slide. Any questions? So, we're gonna just for this class today. We're gonna go back to machine. So we'll talk about principal stress, principal strain, and low stress and shear stress. Principal stress. We talked about this before, months ago. The difference between pressure and the stress is what? Pressure is acting on a point, right? And the stress acts on a plane. So that's the difference between stress and the pressure. And in three-dimensional world, you have a three orthogonal planes, B, sigma H, sigma H. One and sigma H2. Like for example, if you go outside in the ground, you dig up and sample the soil from a certain depth, then you can estimate, maybe you can guess the volume stress and the volume stress from two directions. Right? So there's a volume stress and the horizontal stress sigma H1 and the other horizontal stress sigma H2. Generally, this is a true triaxial stress condition. True triaxial stress condition can be simplified as this kind of model, where the sigma H1 is same as H2. There's a volume stress and there's a volume stress acting in a radial direction. So these are our rho cosine convention. And there's soil mass component of a certain stress. And if you look at this parallel plane, the blue line, then you can take out the bottom part of this little mass. Like this. And the normal stress, this is the sigma n. Sigma sub n or sigma theta, some people say. And how this direction is defined. So for the normal stress, the compression is the plus. It's a positive value. And tau is the shear stress. And clockwise rotation is the positive value. So clockwise means, imagine that this the bottom half of this mass is hung on a string as a pendulum like this, and if this tau can move this object in clockwise direction, so the clockwise direction, then it's the positive. So if the tau is in this direction, this will move counterclockwise, so that's a negative value. So the point is here. And thinking of the string, and that the material is hung on a string and that moves like this direction, then it's a positive.
그대로 자는 거.
For this one, the upper part, this upper part, and this is the normal stress, and this way. So principal plane is the plane with zero shear stress. There's no shear stress. There's only normal stress. Right? So, and principal stress is that normal stress acting on the principal plane. This is the definition. So, when you look at three-dimensional like ground, the inside the ground, then there's a sigma 1 and sigma 2 and sigma 3. There will be three principal stress. The largest one, sigma 1 is the major, it's called the major principal stress. Principal stress, and this is minor. So in terms of the magnitude, sigma 1 is the largest. And sigma 3 is the smallest stress. So in the ground surface, this is the ground surface. And this is reaction through the vertically. There will be a vertical stress and horizontal stress. One, vertical stress H2. And generally in a shallow depth, sigma H1 is almost the same as sigma 2. So we can divide it to a cylindrical case. And we can imagine a cylindrical sort of mass with a radial sigma H and the vertical sigma B. And we can simplify it into two dimension. There's a sort of mass, D and say we have a soil mass in 2D plane. Sigma 1 is acting vertically, and sigma 3 is the minor principal stress is acting horizontally on a soil mass. And then, if this is the failure plane, blue is the failure plane, we want to find out the normal stress at here and the shear stress on this blue plane, tau theta. Sigma theta. So if you drive the equation from the force equilibrium, we've done it in the fluid mechanics. Sigma 1 plus 1. So, from the force equilibrium of a piece, here you can estimate, you can calculate the normal stress on a plane of each track and the shear stress on that plane using these two equations. And here the theta, is the important thing is to define the theta, the angle of the stress. This is very important rule. In this equation, if you want to use these two equations to find out the shear stress and the normal stress acting on a certain plane, then the theta is determined as counterclockwise from the direction of sigma 1 to the direction of sigma theta, the normal stress. So in this case, what's the theta? From the direction of the sigma 1 here, right? This is the direction, the vertical direction. Vertical direction to normal stress, sigma theta. Sigma theta is acting this direction. So from here to here is the theta, counterclockwise. So from these two equations, the tau theta and the sigma normal stress equation, we can draw a circle that represents the stress of the mass. Okay, intersect the sigma 1 and sigma 3 at the x-axis. And so the radius will be sigma 1 minus sigma 3 over 2, right? From here to here. And here is, let's say that this is the A and B, the point A and point B. And sigma 1 minus sigma 3, that is the difference in the major principal stress and the minor principal stress is called the deviatory stress. What about the center? This is the center. And the location of the center will be sigma 1 plus sigma 3 over 2. So this equation this equation indicates that if you know the sigma 1 and sigma 3 of a certain soil mass, you can find the normal stress and the shear stress of any plane. Right? For example, here, if you can determine the theta, right? And you can plug into these two equations, or maybe the vertical or horizontal or any angle, you can find the sigma theta and the tau theta from this equation. Or actually, this small circle represents the sigma, the normal stress and the shear stress of any plane, or given plane of interest. and it's called the Paul method. So using the Paul method, we can calculate the stress condition on any plane with any angle. Stress condition of the solar mass, it's described in steps, step by step. First is to find the pole of plane, of the original plane, so the O sub P. And to find the pole, so in this small circle, you have to find the pole first, to find out the stress condition on an interesting plane. So first step is to draw a line from a known stress point parallel to plane upon which the known stress acts. So it means, let's say that we know the sigma 1, the major principal stress and the minor principal stress acting on a solid mass. In case we can draw the Mohr circle, right? Like this. And the x-axis will be the normal stress flip, and y-axis will be the tau, the shear stress, so the sigma to tau space. Here, draw a line from a known stress. Because we know the sigma 3 is here, and that's acting on a vertical plane or horizontal plane. Vertical plane, right? The sigma 3 is acting on a vertical plane, so we can draw a line parallel to that vertical plane, crossing the sigma 3.0. Then the intersection of the line and a Mohr circle is the pole. In this case, here, this intersection will be the original plane. Or we can start from sigma 1, because sigma 1 is also known stress on a known plane. Sigma 1 is here, and is sigma 1 acting on a vertical or horizontal plane, right? So we can draw a line from here horizontally. Then intersection will be here. So either you start from sigma 1 or sigma 3, you get the same pole, OP. So this is the plane of interest. Then the second is to find the state of the stress acting on the plane of interest. Draw a line through the OP and parallel to the plane of interest. So let's say in this format, we are interested in maybe this plane. And we want to find the sigma theta and the tau theta. Then you can draw a line parallel to this plane of interest from the OP. So I do like this. It's not very accurate, but assume these two lines are parallel. Then intersection with the Mohr circle represents the state of stress inclined at the same orientation. So here, this represents the stress sigma theta and tau theta. So sigma theta will be here, and tau theta. The coordinate of the intersection point tells you the normal stress and shear stress of that plane of interest. And this is the Paul method and the graphical method. So you can use this circle to have a compass at the angle, the device to measure the angle. And you can use the Paul method, or you can use these two equations to get this concept and the concept. What about this stress? then you can draw a line parallel to that is second plane. Then this coordinate, x and y coordinates, it tells you this shear stress and also
그 OP는 무조건 저기.
OP is determined by this normal stress, sigma 1 and sigma 2. So the example is below. So there's two ways you can choose. You can use whole method or you can just use these two equations. Okay, example, the example at the bottom. You have information about the major and the minor principal stress, 52 kilopascal and the 12 kilopascal respectively, and the question is to find the normal stress and the shear stress on this red line plane. This is about 35 degrees conversion. Then let me draw here. This is the circle sigma 3. Sigma 3 is at 12, sigma 1 is 52. And you can draw a line parallel. We need to find the pole, right? Pole will be here. Because if you draw the plane, the line parallel to the plane, actually the sigma 3 is acting. The sigma 3 is acting on the vertical plane. So you can just draw the vertical line. And then it's actually here. So that this point is the OP. And from the pole, you can draw a line parallel to the plane of interest. This is the red line, and this tells you the normal stress and the shear stress. So, if you measure it, or if you use those two equations to get the normal stress of 39 kilopascal and how the shear stress of 1846 kilopascal. Material in math, we know the principal stress 40 and 20 the total and shear stress on this plane here.